Oh, I'm going to start by mentioning that we are having a few issues tonight with our connectivity. It largely comes down to the ISP that we're using to provide us the bandwidth for our rebroadcast server. It is Cox business. Stay away from them if you want good connectivity. So regardless, we're doing a live stream tonight because it's a bit cloudy. We're kind of in the down season right now at Frosty Drew, and we are in a season where we start seeing some clouds. There's snow on the campus. There's ice on the roads in the park here and there. And it's really cold out tonight. So we figured instead of just canceling again, why don't we offer a live stream event? Myself, Mara, Derek, we've all been working on some really great projects this winter and over the late autumn. And we have some really great data sets that we want to kind of show you guys and talk about. And they really apply to what's going on in the sky right now. As we continue tonight, you'll notice on the right-hand side of your chat or your video is the chat window. The chat window is where we're going to be able to ask questions, and Mara will pick up those questions and then read them over the air to Derek and I, and we will try to answer them the best we can, maybe even make something up, right? So we're going to broadcast until about 8 o'clock tonight. I'm sorry we started a little late. That was part of our technical issue. And I'm also going to note that we may drop offline due to technical issues that are ongoing. If that does happen, we'll tune back in next week. So I'm going to turn it over to Derek right now.
All right. I'm Derek, and if you've been out to Frosty Drew, you've probably seen me. I usually run one of these telescopes out in the yard. One of the projects I've been working on this year, started last year, actually during the pandemic, is a giant mosaic of the Andromeda Galaxy. So I'm going to share from my other computer, and we'll see how this goes.
Beautiful. Look at that.
All right. So what we're looking at here is several panels of data, and 19 in fact. I don't have data for these corners because Andromeda isn't part of that area of the sky. So I really tried to capture just the primary Andromeda Galaxy, which is diagonal across the screen. And then above it to the right is one of its satellite galaxies, which is M32. And then this in the corner here, well, below Andromeda is the M110 satellite galaxy. And those are, I might have had those backwards. Sometimes I reverse those because depending on what telescope you're looking in, they flip over. But anyway, so one of the ideas behind this mosaic is in doing a mosaic, we can get a lot more detail in the structure of the dust clouds and molecular clouds of the Andromeda Galaxy. So I've zoomed in, and you can really see how like the detail in the dust clouds that surround the core of the galaxy are captured in doing this type of mosaic. Unfortunately, the center of the galaxy is still, you know, grossly blown out because it's just so dense with stars. And what you can see, like there's some dust lanes that go towards the core coming from the left side as seen here. The other thing that goes on with these mosaic, like doing a mosaic like this, is you can start to capture, you know, a lot of the actual larger star clusters that are in the Andromeda Galaxy towards the outer edges. They're more apparent because they start to dominate the brightness or dominate the data. And then there's another large one up here. Not quite as sharp as I would like, but hopefully with a little bit more processing, I can do that. Each of these panels represents about an hour worth of imaging. So this is 19 hours of telescope time to capture all of these panels, and then to stack them individually, and then to kind of align them up. One of the things that I've been trying to do is to figure out how to go from this, where we have individual mosaics that are pretty obvious as tiles, and then I'm going to slide another picture in here to something that's, far more, blended together. This has its own problems. You might be able to see that, there's some like gradient issues across the center of the tiles, and then the edges are a little bit brighter. And I don't know if that's just noise stack up or what's entirely going on there. Something I'm working through. But it's always fun to show a work in progress. At least I like to. So similar to, zooming in on the individual tiles, we can see that, that all those details are preserved, and you kind of get, one giant picture. So how does this work? We end up using software that you tell it you want to take a picture of M31, and then you tell it you want to do a mosaic that's 6x4, or in this case I think it's 6x5, and it basically creates a job that's all of the center points for all of those tiles, and then each night it'll go through as you're driving the telescope, and it will center the telescope on those coordinates and take the data. Did my computer stop presenting? No, I'm still presenting. Okay. It's just not presenting. Okay, that's just my view. Sorry, I got confused.
Looking good for us.
Looking at my view, I just see me as a sideways head, but that's fine. So one of the other things I wanted to show is what does an individual frame look like as captured by the telescope, and then as we are able to actually generate the stacked up data. What does it look like? So we'll pick one that might be more interesting than one of the edge ones. So like one of the center ones, which so this is kind of what it looks like coming off the telescope. You've got a huge gradient. What you can start to see in the center here, you've got the dust clouds are evident just in the raw data before being processed. But the core is much more blown out, so there's some processing to deal with that. In the histogram, I'll be able to do some live here, but this program allows me to view the data as it comes from the camera, which is, it's a format called bits. But here's the histogram thing, so we can play with this here. Not that it does anything useful. Yeah,
I guess it's good to note too that the object that we're looking at here takes up an area of my cat. It takes up an area of the sky that's equal to the diameter of about 6 full moons. Now you can't see the whole thing with your unaided eye or your naked eye, but you can see parts of it depending on how dark the location is. At Frosty Drew, we can see the Andromeda Galaxy naked eye when we have no moon above the horizon, but you don't see it like this. It looks just like a blurry spot in the sky.
And then this is that same frame that we're seeing raw from the telescope after it's been stacked and had its initial stretch done. So you can kind of see that, the Galaxy M31 in this case does, it's there. It's just very dim and not evident against the in the raw frame. But that's been an ongoing project for a couple of months now. Had to table it for a while because I was getting frustrated with this process going from this mosaic to this blended mosaic, but pick it back up and see where we can go over the next couple months, and hopefully it'll get printed and we'll be able to see it in the Sky Theater at Frosty Drew.
Yeah, when this is done, like this is going to be printable over an area that would be like a wall inside our facility. Like this is going to be a very large print, and I'm very excited about this project.
Yeah. So
We have a question from the chat from Oscar, and he asked, is Andromeda visible all year round?
Andromeda is not visible all year. It is visible kind of in the late summer, early summer, and in the late fall. It's you can see it in the winter months, but it's starting to get a little bit west in the sky, so it's setting pretty early. But it is there. It's if you get far enough north, can you get far enough north to do Andromeda as circumpolar? I don't know.
It's technically circumpolar from our location, but it gets so low to the horizon that you're not going to be able to see it. It'd be like it's like riding the edge of the horizon.
Yeah. So.
And what circumpolar means is any object that is considered circumpolar is above a latitude or an altitude in the sky that from our latitude on Earth, it never sets. So as the sky rotates from the east to the west around the North Star in the north, it'll eventually all the way back around underneath the North Star. So a constellation like Sagittarius, for example, which crosses our southern sky, will rise in the southeast, cross the south at its highest, and then set in the southwest. And then it goes underneath the horizon from our location. The Andromeda Galaxy, being circumpolar, will never drop below the horizon from our location, which means that ideally you'd be able to see it every night if we had a clear sky down at the horizon. An example of a star that is quite visible throughout the entire year is the star Kochab, which is the second brightest star in the Little Dipper. That star is circumpolar, and you can see it all year round.
Yep. One of the other cool things about Andromeda is it actually passes right through the zenith of the sky. So as if you're watching it track across the sky, it'll go basically, or at least from my house, it goes like right through the zenith. I don't know if Frosty Drew is moving far enough south to get between where I live and Frosty Drew that would change. But it's pretty interesting to note when it's basically directly overhead when it's going through the zenith. And it gives the telescope a workout trying to track through that.
And the astronomers, if they're using a Dobsonian.
Yes.
Yeah.
just don't worry about anything within 10 degrees of the zenith.
Now, Mara, do you have access on your machine right now to the work you did on Andromeda?
I can pull it up.
Because Mara did, so Mara is now on the team at Frosty Drew, but this past summer, she was our sole intern for 2020, the year. And one of her projects that she did was data collection and cataloging of the Andromeda Galaxy. And if she has that data set, I'm sure she'd love to show it because it came out awesome.
Yeah, let me just pull it up.
Sure.
Well, just one last thing about the data set that I did while Mary's pulling this up is I did no color, just broad spectrum data collection. No filters in front of it, just a camera that collects, light from infrared all the way to UV, full spectrum.
Now that's the ASI 1600 you have, right?
Yeah, the 1600.
Yeah, so this is Mara's version of the Andromeda Galaxy. And Mara could speak to this more than I can, but I know her capture process was similar to how Derek did it, just without the mosaic.
Yeah.
So you want to talk a little bit about how you did your capture, Mara?
I guess so, sure. So I captured it all in monochromatic, right? Yeah. Used a filter wheel in order to separate out the luminance, the red, the green, and the blue. And then from there, I continued on a similar process that Derek did with stacking all the images and putting it up into one image to get what I have right now. And I think this is about 3.5 hours of exposure time.
So what Mara's describing is how you capture a color image, a true color image, using a black and white sensor. So she's using practically the same sensor that Derek has. So we use the ASI 1600 mm Pro as well. But in this case, so Derek was captured. So Derek's mosaic is much larger than Mara's capture. Mara's image here is the size of a typical image, where Derek's is the size of a typical wall. So in Mara's image, what she did is she used filters to isolate the different colors over top of the monochrome sensor. So using the filters, when she's looking through the red filter, only red light makes it to the monochrome sensor. So she captures a lot of data in red. Does the same for green, does the same for blue. And then she does it in luminance like Derek did, where you don't use a filter. You just capture all the light available. And then what Mara does is when she processes her data, she maps each of those black and white images that were captured through the different filters to their corresponding channels in an RGB image, which stands for red, green, and blue. And when you do that, you end up with a true color image because the wavelengths you're capturing with those filters only represent the color that you're capturing. Anything you want to add about this, Mara?
Not really, I don't think. I think everything was hit for it.
If you looked in a telescope, it would look more like Derek's image than it would look like Mara's. And that's because the object is just a little too dim for they're called our cones. And it's what gives us our day vision on our retina. Our cones are not very sensitive to low light. Our rods, alternatively, are what we use to look at very dark landscapes or look around in the dark. And your rods don't see in color. They see in grayscale. So looking in a telescope, you're largely using your rods to observe those very distant photons of light. And you would see that grayscale or black and white type view of the Andromeda Galaxy, and you would miss out on the colors. The larger the aperture of the telescope is, the higher the likelihood you have of actually starting to see some of those colors. So I got some things here too. I'm going to throw up a project that I've been working on. So I've been working on a part of the sky called the Orion Molecular Cloud Complex. Now, in the constellation Orion, you have let me see if I can bring it up real quick here in Stellarium for you. Stellarium often crashes my live stream. So if it does, Derek and Mara will take over until I get back into the discussion. But what I'll do is I'll try to bring up Orion for you guys here without blowing up the world. All right, so let's see. A window. Is it here? No, I'm going to try to do the screen. All right, prepare yourself, Derek. I have a feeling it's gonna crash.
Here we go. Oh.
All right, can you see it?
We can see a mouse and a black window.
You don't see Stellarium?
No.
Okay, so let me see if I can minimize it. No, Stellarium doesn't like being minimized. Okay, so let's do this. I will stop sharing. And then we'll bring up some of the images themselves. But first, I'm going to kill Stellarium. This is Linux, so that's what you do. You kill your processes. And I think that's rightfully named because usually you do it when you're upset. So here we go. I'm going to show you now a tab instead. So the Orion Molecular Cloud Complex is comprised of the entire constellation of Orion. Now, in the constellation of Orion, you have obviously Orion's Belt and you have Orion's Sword. These two regions are most notable by those three stars that you see in the wintertime, Orion's Belt. Now, what we're looking at here is largely a panoramic, like Derek has done, of these two regions. So the first region up here would be along Orion's Belt. Now, this is the left star Orion's Belt here, Anutak, and this is the right star, or the middle star, Mintaka, with the right star being all the way up over this way. And then this, if you follow the line below the belt, you run into Sigma Orionis, and then into what's known as Orion's Sword. This would be the top star in Orion's Sword, the middle star, and then the bottom star. So let's switch over here to each of these images individually. So in this case here, this is right along the belt. So here's the belt stars again, Alnitak, Mintaka. And you got some really great objects here. For one, you have, this is the Flame Nebula. You have the Horsehead Nebula right here. And all the reds that you see in this image is all excited hydrogen atoms. So what's happening here? That's really the big question, because there's a lot to look at. So one thing that's a good note here would be that you have this star here, Alnitak. Left star in Orion's belt is largely part of the Orion molecular cloud complex. So this is a really bright star. It's a blue star. It's very hot. And the star is casting a substantial amount of light into the gas cloud, but most of the light isn't really interacting with the gas cloud so much as the ultraviolet radiation that's coming off the star. Now, this star is releasing so much ultraviolet radiation that it's exciting all of these atoms. What it's doing is that ultraviolet radiation, it strikes the hydrogen atom and it ionizes it. So ionization, you blast the electron off the atom, and the atom gets, in this case, a negative charge. Now you get those free-flowing electrons, right? They're going to want to reconnect with their ions. They don't reconnect with the same ion, but they will reconnect with another hydrogen ion. And when that happens, they move into a state of excitement. And when they reduce themselves down to a ground state, they release a little bit of energy in the form of a photon. And we can see that, and it happens to be in a red spectrum. Now, when you look at this region right here, and then the Horsehead Nebula right here, what's happening here is all of this hydrogen gas is being ionized and then recombined. It's very excited. But the Horsehead's a little bit closer to us than all of that activity. So the Horsehead appears just as a dark silhouette against all of that activity. And that's how we see the Horsehead Nebula. So the Horsehead would be considered a dark nebula. And it's a region of hydrogen gas that's not actually interacting with any specific starlight or star radiation. So it appears just dormant. And in this case, it forms the shape of a horsehead. Now, I could try to increase this a little bit here. Is it zooming in, Derek?
Yep.
All right. So here we can get a better view of the horsehead. This is still a very low res image here. If I had a higher resolution image on my laptop, you would actually get a much better view of the horsehead. And these little clouds here, this is all the same area, the same hydrogen cloud, but you have little stars that are sitting in here that are actually inside the nebula, and their starlight is shining on the parts of the nebula that surround them, causing it to glow, and that's called a reflection nebula. Now, if you look right over here, you have a series of stars. You have a couple stars in the middle here, and you have a star right over here on the side. This is actually a 5-star system called Sigma Orionis, though we're not going to be able to see all 5 at this exposure. Now, this is a really great region of the Orion Molecular Cloud Complex, and you don't really see this with your naked eye. The Flame Nebula right here, this is another good example of that nebula being closer to you and farther away. So what we have here is, again, we have a lot of this hydrogen gas being ionized by the starlight from Alnitak. But closer to us than Alnitak, we have a bit of the nebula here. Now, it's not a different nebula. It's all part of the same nebula. And Alnitak is embedded in the nebula, or the complex. This part of it right here sits closer to us. So it's not, the other side is what's being ionized. The side we see doesn't look like anything's going on. And it forms the shape of a flame, I guess. When you look at it in a telescope, it looks more like a flame because you see the outline of it here, and then you can see all the dark nebula inside of it. you miss out on a lot of this little wispiness and the colors in here. And then as you look around this field too, you notice that there's a lot of this, it's kind of more white, almost bluer types of the nebula here. And this is called the integrated flux nebula. And the integrated flux nebula, which you're going to see much more in the next image, is largely just a background bit of hydrogen that's not being illuminated by any one star, but by all the stars in the galaxy. So I'm going to load up another image here real quick for you guys. So this is the Orion Nebula. So in this case here, we are looking at this sword region. You guys got it?
No, it didn't load.
All right, let me do this real quick. Share this tab. How about now?
There you go. Yep.
Okay, sorry about that. So this is not just, this is the Orion Nebula right here. This large wispiness right in the middle. Derek, what I'm doing is, can you see my mouse?
Yep.
All right, good. This up here is called NGC 1977. Some people call it the Running Man Nebula. I've heard it called several things, some of which I won't repeat, but I just call it 1977. And this makes up the sword of Orion right here. Top star, middle star, bottom star. And this is really, it's not, you can call it the heart of the molecular cloud complex. And it is kind of in the center of it, but it really isn't the driver of the complex. This is just part of the complex. But in this case, this is the closest site of massive star formation to the solar system. And it's also one of two naked eye visible star-forming nebulae in the northern hemisphere. This is a very common target that we look at it, Frosty Drew, during this time of the year. Now, as we zoom in on this object, you'll notice that there's a lot going on here. It's more than just, you know, a cool nebula sitting in space. This region here is very overexposed. This is called the trapezium region. And right in this area, you have about there's 6 of them, but 4 of them are very high mass stars that have such intense stellar winds that they've blown away all that hydrogen gas from around them, and it actually emerged a little early. And they're the reason why you have this large, almost like a perimeter right here, and it's all blasted out over here. Those stellar winds are starting to blow all that gas away. And they've created a rather large opening in the nebula. If you were to take this and look at it from this side looking in, you would have a very large cutout right in here where it would drop really low. And then you would just see the trapezium stars sitting out there, buffered against all of this nebulosity or nebula behind it. Now, there's about 700 stars that currently exist inside the Orion Nebula. They're newborn stars. They're young. But it has enough mass to form about 2,000 stars before all those stars blow the gas away. In the image, the blues and the grays you see here, this is largely all the starlight being reflected from these very bright trapezium stars. And then all the reds in here is, again, that ionization and then recombination of hydrogen atoms. Now, when you get up to this region here, a little bit further up, when you get into the Running Man Nebula or the NGC 1977 Nebula, this is more of a reflection nebula, which is why it's much bluer. Most of what you see here is just part of this molecular cloud is passing through this rather small open star cluster right here. And the starlight from those stars are shining on it, illuminating it. Though there is a little bit of ionization, which is why we see the reds in here, but it is very minimal. Looking around this object, you have a substantial amount of just hydrogen gas sitting out here. And you have a lot of that integrated flux nebula too. You'll notice on this side over here, there's a lot less gas. This is more just the integrated flux nebula. But over here is a lot more of that Orion molecular cloud. This project, or the goal of this project, is to create, as Derek's doing, a mosaic of not just this region here, but the entire Orion molecular cloud, which takes up almost the entire left side of the constellation Orion. I was hoping to complete it this year. At this point, I really don't think I will. But if we can get a good bout of clear skies and I get out there and freeze, we'll be able to pull it off.
That is the one benefit to Andromeda over Orion is Andromeda you can do when it's warmer.
Yeah, right. I mean, Andromeda is those really awesome autumn nights where you're just sitting out laying on the hood of your car enjoying it. Doing this time of the year, I'm out there a lot. If you guys have been to Frosty Drew, I'm sure you've met our team member, James. And James and I are often out there, and Mara when she's home, freezing in the cold, laughing at everyone that shows up incorrectly dressed and leaves, and they leave in like 5 minutes. So if you guys don't have anything else, I'm going to show something else. Is that cool?
Go for it.
All right. So this here, this is a really great target for this time of the year because this raises kind of a, let me see here. I got so many tabs open now. There we go. Markarian's chain. All right. So this here is called Markarian's chain. And as we move into, we're in the middle of the winter now, we're starting to move closer to spring. We're getting into the time of the year that we call galaxy season, which is largely the spring. And we call it galaxy season because a region of the sky that sits right just beyond the tail star of Leo, which is called the nebula, right near the top left star of Virgo called Vindamayatrix, and then a constellation called Coma Berenices, which is not easily seen because most of the stars in it are very dim. These three regions of the eastern sky this time of the year form a triangle. And in the center of that triangle is the Virgo supercluster, or the center of the Virgo supercluster, which we're part of. And we're talking a cluster of thousands of galaxies. So this time of the year, you can point the telescope into that area of the sky, and you can see several galaxies in just one field of view. And this is a good example. This is called Markarian's chain. And in Markarian's chain, this is all within the field of view here. You have several large galaxies. Now, if you get closer to this image, you start really getting into it, you'll notice that just the chain itself is not only galaxies that are in here. You also have all galaxies in a background over here. A lot of what initially looked like stars are actually galaxies. And this is really quite a fantastic object to not only look at the telescope at, but to work on from an imaging perspective. I mean, you got these on-edge spiral galaxies back here. You got these very irregular shaped lenticular galaxies, another irregular galaxy. These here are called elliptical galaxies. This is another spiral way in the distance back here. This is a galaxy. This is a galaxy. I mean, they're just everywhere in this region. These here are on-edge galaxies. So when you think of a spiral galaxy, so you can find a good face on it here. A spiral galaxy would be defined as and there's none in here, like the Milky Way, for example. If you were looking at the Milky Way galaxy from the top down or the bottom up, you would see that bright galactic nucleus in the middle and the bar coming off of it. And then you would see the spirals come off the bar. And it looks really grand, really awesome. Sometimes it's called a grand spiral galaxy. But if you flipped it on its side, it would look just like a thin line with a bulge in the center. And that bulge is the galactic nucleus. And what you're looking at is the galactic plane. With elliptical galaxies, there is no galactic plane, so to speak. They're round. Well, no matter which way you look at them, you just might change the ellipse a little bit, but there's no plane you're going to look at. It's just a bulge. When you're looking at spiral galaxies on their edge, this is what you're seeing. So in this case, we're looking at spiral galaxies that are not face on for us, but they're tilted from our point of view. And right in here you have, this is an interaction we're looking at here. So these two galaxies are getting very close to each other, and they're starting to interact with each other. And when you think about the future of the Milky Way, and even the very immediate future, we have satellite galaxies around us as well. One's called the Sagittarius Dwarf, one's called the Canis Major Dwarf, one's called the Large Magellanic Cloud, and one's called the Small Magellanic Cloud. And we're going to absorb all of these galaxies and make them part of the Milky Way. And we're currently absorbing the Sagittarius dwarf galaxy and the Canis Major dwarf galaxy. And then down the road, Andromeda is going to come along and scoop us up because Andromeda is bigger than we are. And it's not like we're just going to merge right in and everything's going to be, you know, hunky-dory and awesome. When we come together with Andromeda, both these galaxies are going to get ripped apart. And all of these stars and this molecular hydrogen gas and all of these white dwarfs and black holes and even the supermassive black holes in the center are going to get scattered all over the place. Those two black holes are eventually going to coalesce into one, and all of that matter is going to reorganize into a new galaxy. And that's kind of what you're seeing right here. You're seeing the very beginnings of that as these two galaxies start to interact with each other. And this galaxy is starting to lose its shape, and a lot of its matter is getting kind of tossed off into the space around it. There's another project in this region I've been working on. I don't have any data on it yet because I have data, it's just not processed. And it's called the Coma Cluster. It's another section of the Orion Molecular Cloud Complex, which resides in the constellation Coma Berenices, and it's another cluster of galaxies. Let me see what else we have here in this region of the sky. So we were talking about galaxies that are combining. They're where they come together and form a new galaxy. And there are much better examples of them out here than this, but I will use this one nonetheless. So this image here, this is an image of a galaxy called the Messier 64, the Black Eye Galaxy. And this galaxy is, at first glance, you say, well, yeah, it looks great. You know, it's a nice spiral. You've got a nice dust lane in the center, but you get this little weird thing going on right here. But aside from that, it looks pretty normal. But you know what? This galaxy is not very normal. This galaxy is a product of two galaxies that have come together, but they're no longer in disarray. They're actually now starting to enter the stage of the new formed galaxy. And what we're seeing right here is all of this blue light. These are all the light of young stars that have formed in this new galaxy. And you still have some irregularities in the outer edge of the galaxy, and the spirals are just starting to become more visible. So when you look at the center, this really dark dust lane, which is what gives it its name, the black eye, because when you look at it in a telescope, it looks like a black eye. This is actually a significant amount of hydrogen gas, we call it dust or a dust lane, from one galaxy that has settled over top of the new galaxy, and it hasn't fully merged in yet. So as the new galactic plane is functioning beneath it, I mean, this is hundreds of millions of years here, but functioning beneath it, that dust lane is settling into it. And from our vantage point, which is not straight down from the top, it's kind of off center or off axis, we see that dust lane that sits over top of that central region. And this is also part of the Virgo supercluster as well. This is an object we frequently observe at Frosty Drew, usually in the springtime. In the winter, when we're not, in COVID-19 mode, we'll stay out pretty late into the morning hours with the public, and we'll observe things like this. All right, so how are we doing over here? So got some, I'm reading along right here. Yes, binoculars. Binoculars are a good way to start. Way to go, Mara. So so speaking about the, it's set up their own telescopes in the Niagara Park area. So park closed at the sunset. Okay, so 72 Mustang 351C has asked, is it permitted for people to set up their own telescopes in the Niagara Park area? Is the park closed after sunset? So the general answer to that, Mustang, is yes. Yes, the park is closed after sunset. yes, you can set up your telescopes in Integrat Park after sunset, as long as you understand that you're a guest, and largely a guest of our astronomers. So on the non-public nights, we are working at the observatory when the moon's not out, and having white lights on campus will affect our work. So if you bring a red light, if you're mindful of your headlights when you're driving in, then it's not a problem. You got to respect, you know, obviously the pandemic, social distancing regulations. What you can't do is bring your telescope out on a public event at Frosty Drew. So, for example, Friday nights when we're open to the public, you will not be able to bring your telescope out. And normally we would say, absolutely bring it out on a public night. We would love to see your gear. We would love to talk about it. The reason you can't do that now is because we have a very specific process we need to follow in regards to how we operate our telescopes during the pandemic, because the eye is a known transmission vector of the virus. And when we look through our eyepieces, our astronomers, and probably you with your telescope, understand that you don't want to be stuffing your eyeball into your eyepiece. But your average visitor doesn't understand that, so they're just, bang, they stick their eye right into it. So we've created specific devices to protect people's eyes from our eyepieces, and then we can clean off those devices instead of damaging our optics. We can't vouch for any telescopes in the public space that don't belong to us, and we do not want to be propagating any transmission of the virus on site. So that's why I say if you want to come out on a night where we're not doing a public event, that's totally cool. Just don't leave trash in the park, don't bring white lights, and be mindful of your headlights. Regarding our live stream tonight, so we really enjoyed doing our live streams last summer, last spring during the lockdown, and we've had a lot of requests to bring them back. So what we're doing this year is we're starting to work on the idea of not only trying to put out a live stream on the nights that we're closed at the observatory, but actually trying to host a live stream alongside our public event at the observatory every week, where Derek would manage largely the live stream event feed for now, and we would pass it around to the team. And then at the observatory, we would have our astronomers plugged into the discussion as well, and we'd be able to show live views from the observatory, be able to see what's happening there, and you wouldn't have to worry about going out to the observatory in the cold. And you would also not have to worry about going out to the observatory if you are in a high-risk demographic in regards to the virus where you're afraid of putting your safety at risk. So it gives you an opportunity to still stay connected. I'm not sure how soon we'll see this, but I'm hoping to see it within at least the next month. Now, I don't know if Derek wants to talk at all about the new telescope we're getting.
So, yeah, put me on the spot. So, as many of you know, we have a 16-inch Meade telescope at the observatory in the dome at Frosty Drew. This would, I think, be its 21st year.
It is 21st year.
So, we're going to have a send-off party for it at some point, and it's going to be retired from its current use, but I think it's going to get reused as another instrument within the program, but it's probably going to take a break for a little while we figure out some of that engineering. But in its place, we have gotten a 24-inch corrected Dow Kirkland telescope, or CDK for short, which is a slightly different optical design than what's there now. What's there now is a Schmidt Cassegrain design, and you know, so it's a 16-inch what's there now, and we're going to have a 24-inch there, replacing it going forward at some point late this year / early next year. The timeline is still somewhat unknown. But that's at least the process has started. So we're very excited to see what that brings to our viewing capabilities, and also to our data collection capabilities, because we have from the get-go selected equipment that allows us to do data collection instead of trying to augment it or modify the equipment that we already have. So that's going to be super fun, super exciting, and can't wait for first light on that. But I think it is going to mean we're going to be shut down for a little while that installation takes place. I'm not sure right now if we're going to continue to hold our public nights and just have the telescopes out in the yard with tours of the dome in its state of transition, disarray, or if it'll remain closed. But we're always interested to keep the public in the loop, since it is the public that keeps us going. So definitely looking forward to having that instrument for all of us to look through on our public nights.
We're very excited about this new telescope, and it's a project that Derek and I have been working on, and it's been something we've talked about for many years, getting this telescope. So this is something that we were very excited and surprised when we found out that we're actually able to do it this year. And we're going to try to do a lot of cataloging with the installation. We're going to have the whole thing. We're going to have a videographer do the entire installation, a photographer out there. And we're going to really make a spectacle out of it. I mean, there's nothing like drama, right? So we're going to really try to have you guys involved as much as we can in the installation of that new telescope. But if you guys have been to Frosty Drew, and if you think the telescope in the dome right now looks big, wait until you see the new one, because it's about
won't fit through the door.
Yeah, it won't fit through the door. Exactly. We got to bring it in through the roof when we put it in. So that's how big this thing is. So that is awesome.
We might have measured after we placed the order.
Yeah. I was texting with Derek when I measured the door, and I was like, dude, it's not fitting through the door. We're going to the roof. So we were like, yay, that's great. So we're going to leave you guys right now with let me see here. What do we got? One more image I'm going to bring up, and I'll show you. Let's do this. The galactic nucleus. Because the galactic nucleus, for those who are really into the Milky Way, the Milky Way's galactic nucleus just became visible. And we don't really start looking at it at Frosty Drew until April, but it has become visible already. So this is an image of the Milky Way galactic nucleus from Frosty Drew in 2019. There we go. Now, this is a morning in April, and I encourage you to visit as often as you can on the moonless mornings in April to catch this view. It's usually around 3 o'clock in the morning where it starts to really open up, and through May it continues to become visible. Now, our team member James, who is not on tonight, he is the de facto Milky Way hunter. To tell him, yeah, we're going to wait until spring, he'll scoff at us. He doesn't wait until spring. He goes out now to try to find it, because you can. If you have the right location and a low enough horizon and a lack of light pollution in the very, very early morning hours before pre-dawn kicks in, you can see the Milky Way rising over the ocean. And the region you're seeing is largely this region right across here and up. And you kind of miss out on this, but you see it a little bit. And James has already started capturing images of this. Now, I don't have any on me to show you tonight, but that means that Milky Way season is kicking in. Now, at Frosty Drew, the best time to see it, I guess in a family-friendly type time frame, would be in July. July at Frosty Drew, the Milky Way will be visible right after astronomical twilight ends, which is roughly around 9:30 p.m. But you can see it at Frosty Drew in the morning hours starting in April, early April, and it will continue through August, the views at Frosty Drew. So get excited about it, because Frosty Drew is the darkest spot in southern New England, and it is one of the spots where you can see the Milky Way very easily with your own eyes, not with a telescope, over the camera. And it is quite compelling when you see it there. And I mean, I've been at Frosty Drew for many years now, so is Derek, and we'll both tell you that every time we see it, we're all like, wow, look at that. Like, it's almost like the first time you're seeing it. So get excited for it. And we're going to pack up now. And I know you guys got the shaft on the first 10 minutes, but that's life, right? 5% of your life you can't change. Use the other 95% to make it work. I guess you can say that. But regardless, we're going to continue to try on-site events. Right now we are in our down season. So our on-site events currently do not require tickets. It doesn't mean it's going to stay that way. It really depends on how many people are coming out. But as long as we can manage a cap of less than what we have to cap at right now, which I believe we can cap at like 250, but we're not going to get anywhere near that. You know, our cap usually sits around 90, our max right now. It's what we feel comfortable with. And as long as we can keep below that number, then we will continue to offer events every week without tickets until the season and until the summer season starts to ramp up. Additionally, we are in our recruiting season right now. This is when we're looking for interns. This is when we're looking for volunteers to join us this summer. So if you're a physics major, if you're a math major, if you're an engineering major, Mara's a physics major. She's actually at school right now tuning in. If you are a high school student that's just got a thing for math, got a thing for science, get in touch with us. Astronomer@frostydrew.org. Write us an email, tell us you're interested. We'll ask you some questions, send you the application kit, and we'll take it from there. So we were happy to give you a live stream event tonight at least. Next week, if we're not open on site, we're going to try to do the live stream again. And we'll continue to post updates to our website and our social media on what we're doing. So until then, have a really great night.